Hey dude, check out what I just found in the attic.
Whoa, what is it?
I don't know, it's just some...
It's not in English. I don't know. Let's put it in and see what it is.
Stop right there, evil scum. You return those animals to whence you got them.
Vectorman! You will not defeat me! It is too late! There's nothing you can do about this! These are my dogs! Defeat me! There's no way! I will have my revenge!
Oh boy, Vectorman, thanks! But how did you know how to dodge those bombs? Oh, that was easy. Don't worry, I can have my friends over at Khan Academy explain to you. So, I'm sure you're all wondering how Vectorman does all of his superpowers and stuff. I think you'd be shocked to find out that he doesn't actually have superpowers. He just does math. So what I'm going to show you today is how Vectorman knew how to dodge all of those bombs. So he used vectors. So we're going to use this problem to illustrate a vector and show you how to do them so that you can be like Vectorman. With this problem, we're given a moving particle has position x of t and y of t at time t. The position of the particle at time t equals 1 is 2, 6, and the velocity vector at any time t is greater than 0 is given by 1 minus 1 over t squared and 2 plus 1 over t squared. First problem is to find the acceleration vector at time t equals 3. So to do that, we get x of t equals 2t to the negative 3. That's the derivative of this. Then we do y double prime of t is equal to negative 2t to the negative third. And that's the derivative of this. Because we were originally given velocity vectors, to find acceleration, all we have to do is take the derivative. So once we've found both of our acceleration vectors, we can plug in 3 to solve for what our acceleration at t equals 3 is. So x double prime of 3 is equivalent to 2 over 27. So now we plug into the y equation. So y double prime of 3 is equal to negative 2 over 27. So in vector form, we have x double prime of t and y double prime of t when t is equal to 3. So that gives us 2 over 27 negative 2 over 27. And that's our acceleration vector at time t equals 3. Now we'll move on to part B, where we can find the position of the particle at time t equals 3. So that means we need to integrate both of our vectors, because velocity is the derivative of position inverted position is the integral of velocity. So we have x of 3 is equal to 2 plus the integral from 1 to 3 of 1 minus t squared dt. The reason we're going from 1 to 3 is because we're given that t equals 1 is 2, 6. So this 2 is our starting x coordinate, and then we know its velocity from t equals 1 to t equals 3. Also, we have our y equation. Y of 3 is equal to 6 plus the integral 1 to 3. For the same reasons as x, we know we're using 6 because that's the y coordinate we're given as our initial coordinate. 1 to 3 of 2 plus t to the negative 2 dt. These are our two position equations, and they will give us our position at t equals 3. Now we evaluate. So we have 2 plus the quantity t minus 1 over t from 1 to 3. Continuing with that, we can find that we have 2 plus the quantity 3 minus 1 over 3 minus 1 minus 1 over 1. That solves out to give us 10 over 3. So our x position at t equals 3 is 10 over 3. Now, to do our y one, we're going to follow the same process. We're just going to solve the integral and find our answer. So we have 6 plus 2t minus 1 over t evaluated from 1 to 3. Plugging in just like we did last time, we'll get 6 plus 6 minus 1 over 3 minus 2 minus 1. That solves out to give us 32 over 5. So our y coordinate at t equals 3 is 32 over 5. Put together, we get x of 3 and y of 3, and that is equivalent to 10 over 3 and 32 over 3. Now we're going to move on to C, and we're looking for the time t when the magnitude of the velocity is 8. So to do that, we're going to do dy over dx, and that's equivalent to dy dt over dx dt. So that's going to be equivalent to these two numbers here, because this is our dx dt and this is our dy dt. So we're going to put one over the other and set them equal to 8 and then solve for t. So that's 2 plus 1 over t squared over 1 minus 1 over t squared. And that needs to be equivalent to 8. So, in order to do that, we're going to solve for t. So first we'll multiply by the denominator and get 2 plus 1 over t squared is equal to 8 minus 8 over t squared. Get everything on the same side, and we'll have 6 equals 9 over t squared. That solves to t is equal to the square root of 3 over 2. You can plug that in to the original equation in order to check for accuracy. On to the final and what is probably the most easy part of this entire assignment in terms of the actual work you have to do. We're going to be finding the slope of the line as t approaches infinity. So that's going to be the limit as t approaches infinity of our dy dt, because we're still looking for the magnitude of the velocity. So we'll have 2 plus 1 over t squared, all of that over 1 minus 1 over t squared. And that is equivalent to 2. Because as we go to infinity, both of these t's will go to infinity. Our second terms will zero out and we'll be left with 2 over 1, which is equivalent to 2. So the slope of the line as t approaches infinity is 2. Now I'm going to show you all of the answers together. Here are our final answers. The acceleration vector at time t equals 3 is 2 over 27 and negative 2 over 27. The position of the particle at time t equals 3 is 10 over 3, 32 over 3. The path of the particle has a slope of 8 at time square root 3 over 2, and the limit as t approaches infinity of dy dx is 2. So that's how Vectorman knew where the bombs were going to be thrown at him. He could see how the villain was throwing them and calculate all of this in his head. As you can see, all you gotta do to be a superhero is be really good at math. Thanks for watching.